what we just saw from the last discussion is that if you have impurities added to a semiconductor crystal in such a manner that you replace the silicon atom with the impurity atom, it could be phosphorus or it could be arsenic, you will basically create a level which is very very close to the bottom of the conduction band. Okay, and this level we call it as ED, okay, or donor impurity level. Okay, ED is called donor impurity level. And then normally when you add the impurity atom, electrons will be there in that each state there is a one electron, and then what we looked at is like what happens to that electron. Can we find those electron there itself, or will it be in conduction band? And what we found out that none of those electrons at room temperature stay in that ED level. They basically go to the conduction band. Okay, so conduction band is starting from EC. So most of them, most of these electrons, almost all of them, you can say, are not found there. Okay, if you take 1000 such electrons, out of that 996 electrons at room temperature, that means almost all of them so goes to the conduction band. Okay, so some of them might have gone to the valence band also, but out of the total electrons which are there in the conduction band plus the donor level, very less fraction, maybe 1 out of or 4 out of 1000, that is the number that we got stays. So how they have gone, where they have gone, we do not know exactly. So it may not be correct for me to say all of them gone to the conduction band. Some of them might have gone to the valence band also and joined with the holes there. Okay, destroying the holes. So it could be like this also. But the point is that they don't stay occupied in the ED. Okay, so donor level is almost empty. Okay, they don't have any electrons. Probably most of them have gone to the conduction band, and the rest might have gone to the valence band, but the donor level is almost empty. Okay, so we have seen the occupancy of ED level, okay, is negligible. Almost all the electrons. So by electrons I am basically adding N0 plus Nd. Almost all the electrons are in conduction band. That is N0 or you can say Nd is negligible. Okay, so N0 plus Nd is almost equal to M0. So that's what we have seen so far. Okay, there is a reason why we are looking at these things, so that I will come into. Now similar picture exists in the case of adding acceptor impurity. We can also talk about similar things. Say if I add acceptor impurity, then I will create a level which is just above the top of the valence band. So I will create a level like this here, very very near. Okay, so this is my EC, this is my EV. I am drawing band diagram, not band structure, and this level is called EA. Okay, this level is called EA, and a similar analysis I can do, but now I will see the vacancies of vacancies in the acceptor level. Okay, so here I have looked at the occupancy in the donor level, look, occupancy in the donor level is what I looked at for n-type impurity or n-type material. Now I am looking at the p-type material where we are adding acceptor impurity atoms, and we are looking at, so similarly, if we look at the vacancy of EA level, okay, we will find that out of all the vacancies, or you can say out of all the vacancies are also called holes, okay, out of all the holes, that is P0 plus PA, okay, almost all of the vacancies are in valence band. So what do I mean by that? Just the analogous thing, but here in terms of holes. So whenever we create this EA level, so there is vacancies here. It comes with vacancies. Okay, everything is empty initially, because this is like the state that was created due to the vacancy in the boron atom, for example, or aluminium atom. Now there were a lot of vacancies here due to thermally generated, and then electrons there in the conduction band. And then what happens? So once you create these vacancies here, the electrons which are in the conduction band, they will go to this point, okay, they will get occupied. So whenever they go, they create one additional hole here, because they are getting enough energy to move and occupy this higher level. So they leave behind a hole here. So all these electrons will, and similarly lot of electrons will fall into this. Okay. Lot of electrons fall into this and occupy. Okay. So now these are occupied. Okay. Lot of electrons will fall into it. So because of this, this acceptor impurity level get occupied. So if you count the vacancies here, it is almost negligible. Either they got destroyed because of the electrons jumping from the valence band to the donor level, because it is also very closely spaced. This difference is 0.01 to 0.05 electron volt. So because of that, if you count all the vacancies, that means just like we earlier found the fraction, that is PA divided by P0 plus PA, this will be almost 0. Okay, very negligible, very small fraction. Okay, just like we did. So same analysis, same mathematics we can do, and we will get the same result. Okay. So therefore, we can say that, so this you can say that PA plus P0 is almost equal to P0. So just like I have said here, I can say this here also. Okay, they are analogous explanation. Okay, there is only difference is that we are looking at the vacancies here. Vacancy of EA level, that's the difference. Earlier we looked at the occupancy of the ED level. Okay, occupancy of ED level and vacancy of EA level. Occupancy of the ED level and the vacancy of EA level, they are alike. Okay, and the vacancy here is going to be very small. It is going to be occupied very much. Okay, so by so what does that mean? So that means after adding a lot of acceptor impurity atoms, when you look at these acceptor impurity atoms, they are all having some additional electrons in the acceptor impurity states. Okay, negligibly small number of them are having or vacancies. Okay, negligibly small number of them. Now, so this you can summarize and say that you can summarize and say that so therefore in a compensated, so I will tell what is meant by compensated semiconductor. So compensated semiconductor is a semiconductor in which we add both Nd and Na. That means acceptor impurity as well as donor impurity atom in the same semiconductor. Okay, sometimes that is done. So in a compensated semiconductor, all the donor states or donor impurity states are occupied, so and all the donor impurity states are empty. Okay, all the donor impurity states are empty, unoccupied, and all the acceptor impurity states are occupied. Okay, so in a compensated semiconductor, a semiconductor with both Nd and Na added, so we will have both the donor level and acceptor impurity level, in which case all the donor level are actually empty. That means the electrons have gone to the conduction band, and similarly all the acceptor level in that compensated semiconductor will be occupied. So negligible vacancies. So we are ignoring therefore we can ignore thus we ignore the occupancy of donor level in counting the number of electrons, and similarly we ignore the vacancies in the acceptor level in counting holes. Okay, which is a statement form of what I have put in this box. Okay, N0 plus Nd is almost N0, and Pa plus P0 is almost P0. So it is the same statement that I am making. Okay, so now we do not know where is the Fermi level in an extrinsic semiconductor. So we are actually going to figure it out. And if you figure out P0 and N0, then we can figure out EF. Okay, so that is basically the approach. So first let us figure out what is N0 and P0. So in order to figure out what is N0 and P0, what we do is we consider the charge neutrality equation. Charge neutrality. So the purpose of considering charge neutrality is to figure out the number of majority carrier. earlier I said if we know the majority carrier, we can use law of mass action to find out the number of or concentration of the minority carriers. So we are going to now figure out what is the number of majority carriers, okay, which is N0 in N-type semiconductor. Okay, so to find N0 in N-type semiconductor and P0 in P-type semiconductor. So they are the majority carriers. Okay, so let's look at. So charge neutrality means that number of negative charge should be equal to number of positive charge. Now what is the number of negative charge? Basically all the electrons in the conduction band, so which is N0. Is there any other negative charge? When an acceptor impurity atom gets occupied, it will have a additional electron. Actually the positive charge is only one lesser than the, if the fifth or the fourth electron comes into the acceptor impurity atoms, it becomes it becomes negatively charged, because it doesn't have any proton to compensate that additional electron that has come into it. So N0, that is the number of electrons, plus Na, which is the negative charge due to the acceptor atoms accepting one electron to it. Okay, we say that we already saw that it will mostly get filled up. So that is equal to number of positive charges, basically the holes, plus donor atom when it loses. We already saw that all the donor atom states are empty, so they all go to the conduction band. So each of the donor atom which loses an electron, because the fifth electron is lost, so it has a positive charge ion. It is like an ion, positively charged ion. Similarly, acceptor atoms are like negatively charged ions. So now to a very good approximation, you can say that from our previous discussion, now you can say that this number of acceptor atoms is basically very much equal to, so if you accurately write it, this is that is N0 plus, so out of Na atoms, some of them have vacancy, which we calculated as Pa, but this number is very negligible. So but if you accurately write it, this is P0 plus Nd minus the vacancies in the donor impurity level is Nd minus Nd minus small nd. Okay, small nd is the number of occupied states in the donor level, which is also negligible. So this is very negligible from our previous discussion. So let me just mention that Pa is negligible and Nd is also negligible from our earlier discussion. So we don't make much error in leaving those. Therefore we can say N0 plus Na. So that is like almost 100% ionization of the impurity atoms. All the acceptor atom is now occupied. So similarly we can say all the donor atom is empty. Okay, assuming complete ionization. So which is true at higher temperature. Higher means that which is almost true at T equal to 300 degree Kelvin. Okay, but very low temperature we need to be careful, which is, this is not true. Okay, but so I have to but cannot be or is not valid, but this is not valid at say at very low temperature, and usually very low means say 200 degree Kelvin or less than 200 degree Kelvin. Okay, so if it is above 200 degree Kelvin, okay, mostly the temperature that we have, the room temperature, even if it is a peak winter, like we may have say 0 degree, which is 273 degree Kelvin. So this is valid. Even like very cold places also we may have some minus 50 degrees Celsius. Even then this approximation is valid. Okay, so almost all the places on the earth you can accept this approximation. Okay, so you can mathematically show at what temperature this approximation breaks down. Okay, so that also you can calculate. But let's assume all the practical purposes the temperature that we are considering, most of the donor impurity atoms are ionized, and that means losing electrons, and the acceptor impurity atoms gets electrons from the valence band, so they are all fully occupied. So if that is the case, then okay, now let's look at whether it is n-type or p-type. If n-type, what is the requirement? We should have Nd greater than Na. If n-type, so let's assume that it is n-type, and then we will proceed with the calculation. We can also do the same calculation for p-type. If Na is greater than Nd, then we will substitute. So if Nd is greater than Na, then we will substitute. Then P0 is the minority carriers. Okay, minority carrier concentration is going to be equal to, we will call it as Ni square by N naught. So which I earlier introduced. So therefore the equation is going to become, charge neutrality equation is going to become N0 plus N0. Okay, so let me write it as N0 equal to P0, I am substituting it as Ni square by N0, then plus Nd minus Na. Okay, I took this Na to the opposite side, so it became Nd minus Na, because I am insisting that it is n-type material, therefore Nd is greater than Na. So I will get the charge neutrality equation like this. So multiplying with N0 everywhere, I will get a quadratic equation, which is N0 square minus Nd minus Na into N0 minus Ni square. Okay, so I just multiplied N0 everywhere, and then brought all the terms to the left hand side, and this is now equal to 0. So this is the quadratic equation I need to solve to find out the majority carrier. N0 is the majority carrier, so our quadratic expression is in terms of the majority carrier. Once I get the majority carrier, I can substitute Ni square by N0 and get the minority carrier. So this is the procedure. So now what is N0? So therefore N0, we know the equation is going to be Nd, so minus b plus or minus root of b square minus 4ac. Okay, so that is Nd minus Na it is minus b. Then we have two solution, that is plus or minus, and b square nd minus na whole square minus 4 a is 1, c is ni squared by 2. Okay, so that 2 I am taking here, and then here also. So this is going to be our expression. Now the question is like if nd is equal to na, I will have intrinsic. Okay, so that is a side note. If nd is equal to na, this will give to intrinsic semiconductor. So I should get back N0 as Ni conductor. Okay, let's see whether I will get back. Nd is equal to Na, the first term goes to 0, and inside the root I will have this goes to 0, and then so it will be okay, there it will be plus. Okay, because this is minus 4ac is going to be negative, so minus 4ac is going to be positive. So so I will get 2 ni square in the root, 2 ni I will take square root and then divide with the 2, and it will become ni. So but only possible if I take the plus root. So therefore I should ignore the negative root. N0 equal to negative ni doesn't make any so physically only the plus root will make us make sense. Okay, the negative root doesn't make any sense because the charge carrier cannot be negative, the number density cannot be negative, so we have to take the plus root. Okay, so when nd equal to na, we will get the intrinsic semiconductor, and therefore n0 should be equal to ni. So we neglect the negative root. So this is the expression for the majority carriers. So it has two components. One is basically the difference between nd and na, the other is the ni, okay, which is the intrinsic carrier concentration. So the majority carrier is going to be determined by these two quantities. One is the nd minus na, and the other is ni. So therefore the conclusion is that the majority carrier concentration, we have looked at the case of n-type semiconductor. Same discussion we can talk about for p-type also. Majority carrier concentration is determined by two parameters, that is number 1 nd minus na, and that is number 1, and number 2 with ni. Ni is basically determined by the temperature, and that is so this is fixed by temperature for a given material T, for a given material, and in nd minus na, this is the doping concentration. Okay, so these are the two parameters that determines the majority carrier. Okay, let's do a problem to look at these numbers. So question: find n0, find n0 and p0 for an n-type semiconductor. So given T is given 300 degree Kelvin, then Nd is given, that is 10 raised to 16 per centimeter cube. Then Na is given as 0. There is no doping with acceptor impurity, only donor impurities are doped, so clearly it is an n-type semiconductor because Nd is greater than Na. So since temperature is given, you can find out Ni. Let's assume that this is silicon, okay, n-type semiconductor. Okay, so silicon. So Ni you can find out by using the formula that we derived yesterday, that is Nc into Nv into e raised to minus Eg by 2 kBT. Okay, so if you substitute the temperature and so you will get it as 1.5. So you have to take the effective mass of electron holes in the silicon semiconductor, so you can get all the constants in Nc and Nv, and then there also temperature is there, and so you put 300 degree Kelvin and you will get it as 1.5 into 10 raised to minus 1.5 into 10 raised to 10 per centimeter cube. So that is Ni. So now and we also have Nd minus Na is basically 10 raised to 16 per centimeter. So these two are the only things that determines our N0. So therefore N0 is equal to Nd minus Na divided by 2. Then we take the plus root and then square root of Nd minus Na okay, that 2 I am going to take it inside, square, plus 4, okay, 4 will cancel with the 2 from the denominator. Okay, what I mean to say is that I am taking that expression that we derived, absorbing the 2 inside. So okay, so it will become Nt minus Na divided by 2 the whole square. Okay, and this 4 will get cancelled with the 2 outside the root. So plus Ni square. So it will be plus Ni square. So all the numbers we require is available with us. So that is 10 raised to 16 by 2, then plus square root of 10 raised to 16 by 2 the whole square, plus 1.5 into 10 raised to 10 the whole square. Okay, so now we need to know the order of magnitude here involved. So the outside term is trivial, so that is 10 raised to 16 by 2, but inside the root, if you look at these terms here, 10 raised to 16 the whole square. Okay, so that is like 10 raised to 32, 10 raised to 32 by 4, plus here if you like it is 2.25 into 10 raised to 20. So when you add something like this, you should have an understanding to compare these numbers in the square root. One of them is 10 raised to 32, other is 10 raised to 20. So if you look at this addition, immediately you should be able to tell that this is so negligible, you don't even need to consider it. Okay, so why? Because if you want to add these two numbers, if you write it like so, this will have 32 zeros and this will have 20 zeros. So when you add, so for example, if you add like 1 with say how will I say, so let's say 10 raised to 3 plus 1 if you want to add. So this is 1 into 10 raised to 1. So this is only just or 10 raised to 0. Okay, so this is only 3 orders of magnitude difference. So you write the first number plus the second number will be something like this. So what you will get 1000. If there is a 5 orders of magnitude difference, like 10 raised to 5 plus 1, then it will be even more trivial. So you put 5 zeros, 1 lakh, and then this, after adding you will get the result like this. So if you have like 12 orders of magnitude difference, you can imagine like you are adding something with 12 zeros and then adding a 1 to it. Okay, 1 followed with the 12 zeros and then adding a 1 to it. Okay, it hardly matters, this addition second time hardly matters, right? So the result will be, if you write it okay, so nobody would want to carry this one around, and you will just take the first number itself as the sum. Okay. I hope you can get what I am trying to say. So this is basically 10 raised to 16 by 2 plus 10 raised to 16 by 2, which is basically 10 raised to 16. So this example demonstrates that you don't need to consider your Ni. If the difference between the two terms are like at least 2 orders of magnitude, you don't need to consider the second term. Okay, so whichever is the higher order in magnitude, this is 10 raised to 16 and this is 10 raised to 10. So this is like many orders of 6 orders of magnitude, so you don't consider. So that is the insight from this problem, that so that is your N0 is equal to Nd minus Na. If Nd minus Na is at least 2 order of magnitude larger than Ni. So that way you can understand that your majority carrier concentration is, so therefore N0 is 10 raised to 16 per centimeter cube. What about P0? P0 is Ni square by N0, and if I take the Ni square, that is 1.5 into 10 raised to 10 square by 10 raised to 16. So which is what? So which is this is 2.25 into 10 raised to 20 by 10 raised to 16. So that will give us 2.25 into 10 raised to 4 per centimeter cube, which is very, very less. So you see that the P0, the N0 is 10 raised to 16 and P0 is 10 raised to 4. So therefore N0 is much greater than P0. Okay, so that is why they are called minority carriers. So this is at room temperature. Now if I increase the temperature, much larger temperature if you go, then the Ni will grow exponentially, right? For every linear change in the temperature, the change in yesterday we did a problem like 300 degree Kelvin and 450 degree Kelvin. There were around 4 orders of magnitude change in the temperature. So that is going to happen with the rise of temperature. Ni is a very strong function of temperature. So since Ni is a strong function of temperature at very large temperature, say something like 500 degree Kelvin or something, the Ni will become comparable to Nd minus Na, then we cannot assume N0 is equal to or the majority carrier is equal to Nd minus Na. Okay, so then we need to use that formula, but otherwise we don't need to use that quadratic solution. If there is at least 2 orders of magnitude difference between Ni and Nd minus Na, then we can just assume that N0 is equal to Nd or Nd minus Na, etc. So if I now draw a graph between N0 and temperature of an extrinsic semiconductor. Okay, so this is temperature. So here I have say 100, 200, 300, 400, 500, 600, 700. Okay, so these are the value of temperature, and then if you draw this curve, so and here on y-axis I have the concentration for N0. So in centimeter is to -3 per centimeter cube. So this is say 10 raised to 12, then 10 raised to 13, 10 raised to 14, say 10 raised to 15, like this. And then if I draw this, what is going to happen is, say at I have a Nd is equal to say 10 raised to 15, 15 okay by 2. Well, that means 5 into 10 raised to 40. Okay, 5 into 10 raised to 40 per centimeter. So if I draw the curve for this particular, so 5 into 10 raised to 14 is somewhere here. So which temperature this concentration N0 is going to be? Just now we found that 300 degree Kelvin. If you find out, it will be here only. So for middle temperature till 200, I said there is no change, but if you go to high temperature, then what is going to happen is that around 500 and all may begin to change. The concentration is going to begin to increase with it. So that is because Ni is going to become prominent. And when you go to the low temperature, what is going to happen is that at very low temperature, say less than 100 degree or Kelvin, so this is in degree Kelvin. Okay, at very low temperature, what is going to happen is that this concentration falls down. And why this is because the states in the donor level will get occupied. Okay, they will not be excited to go to the conduction band, they will be occupied. Okay, they will not be vacant. The empty states will be filled, and then no electron will go to the conduction band at at 0 degree Kelvin. We know that absolutely no electrons are going to be there in the conduction band. All electrons are going to be in the so the Fermi level is going to lie between ED and EC. Okay, at very low temperature, 0 degree Kelvin. So this is like 0 degree Kelvin, where you will have absolutely, but the middle region is called is what we call as the extrinsic region. So the middle region we call it as the extrinsic region, and I can also show the change in the so at room temperature 300 it was 10 raised to 10, right, 10 raised to 10 somewhere here. Okay, so at 400 it may be something like 10 raised to 12, and the Ni will increase like this. And it is this Ni that is making this change in N0. Ni is a function something like this. Okay, to draw it very clearly. Okay, so this is the change of Ni. Ni is a strong function of temperature. As temperature increases, Ni increases by orders of magnitude. So what will happen is that the concentration of electrons, until Ni becomes significant, it doesn't change, but as Ni becomes significant, then it follows this. Okay, so it will be determined mostly by Ni at high temperature. So that region is where we call it as intrinsic. So the N0 at a very very high temperature, it can go to the intrinsic region where it is mostly determined by the Ni. So this is our Ni. Ni is a strong function of temperature. So as T increases, Ni will exponentially increase. Okay, so at around 500-600 degree Kelvin, Ni is going to be larger than the 10 raised to 14, 10 raised to 15, and therefore that will decide your N0. But there is a long range of temperature where the room temperature also comes in. The N0, the concentration in the conduction band, is determined by the doping concentration. It is basically equal to Nd. So here it is N0 equal to the middle region. Okay, the middle region. So this is the region which is called as here. In this region, N0 is equal to Nd. And outside this, N0 is equal to Ni. And at very very low temperature, you have N0 neither equal to Nd nor equal to Ni. It is much lesser than Nd. Okay, so these are the various region of operation of a N-type semiconductor. Okay, similarly you can draw for acceptor impurity doped semiconductor, which is P-type semiconductor. There also there will be an extrinsic region at normal temperature. At very low temperature you have very less number of holes, so you will plot holes instead of electrons concentration. Alright, so finally what I want to say is that once you find out your N0, you can find out your Fermi position of the Fermi level. Okay, by taking the expression so location of EF in N-type semiconductor. So already I told you that it is going to be above EFI, the intrinsic Fermi level. Location of EF in N-type semiconductor. So we have this expression which is we have two expressions. One is N0 is equal to Nc into e raised to minus Ec minus Ef. So if you know N0, you can find out EC minus EF from this expression, or you can write it is equal to Ni into e raised to EF minus EFI. So any of this expression you can invert, and so for example, if I use the first expression, then with respect to EC, where is my, so below EC, how much is my EF? I can find out so there is a KT here, KBT, here also KBT is there. So I can write it as KBT into ln, okay, natural logarithm of NC by N0. Or so this is one way I can specify my location of the Fermi level, or I can say it as EF with respect to how much it is above my intrinsic Fermi level, I can say. Okay, so in that case I will say it as KBT natural logarithm of N0 by Na. So both either way I can specify. So once I have N0 computed, that is my majority carrier computer, then I can tell either how much it is above the intrinsic Fermi level, or I can say how much it is below the bottom of the conduction band. Okay, EC minus EF I can find out, or EF minus EFI, how much it is above the intrinsic Fermi level. How much EF is above intrinsic Fermi level. So this says how much below the bottom of conduction band. Okay. So both way I can specify this. So EF will be determined by two things. One is N0, and so if you look at the second expression, it is very clear that EF, location of EF is a function of Ni and N0. So therefore the location of EF in N type is the same discussion I can talk about with respect to P type also. So there we will either say with respect to EV how much it is above EV, and also how much it is below EFI. So that is how we specify. So the location of EF in N-type semiconductor depends on two things. One is Ni, and other is N0. Okay, so intrinsic carrier concentration and the concentration of electron in the conduction band. Okay, so now Ni will depend upon temperature. Ni will depend on temperature, and N0 will depend upon both temperature and the doping concentration. So therefore indirectly I can say that or EF is a function of temperature, because Ni will depend on temperature. The other is Nd minus Na. Okay, EF is a function of both doping concentration, that is Nd minus Na, and the temperature. So let's see how does it varies. So if I fix the temperature, then I can talk about how it varies with the doping concentration. So if T is fixed, then EF only depends on the doping concentration, that is Nd minus Na. Okay, so that I can show. So if I take a energy E in vertical axis, and then I draw my EFI here, that is the intrinsic concentration, and then on the x-axis I take Nd minus Na in centimeter raised to minus 3. So what will happen as I increase, say 10 raised to 12, 10 raised to 13, these are the typical doping concentration, 14, 10 raised to 15, 10 raised to 16, 10 raised to 17, anything above 10 raised to 17, they are like heavy doping. Okay, that also is done sometimes. Some of the devices make use of that. So what is going to happen? So as I increase the Nd minus Na, how does the Fermi level change? So I am plotting basically Fermi level change as a function. So suppose this is my EC. So this is EC. So as I make more and more n-type, what will happen is that it will go more and more near to the conduction band. So let me use a different color. Say it is very close to, so at say 10 raised to 11 at room temperature, if I say so this is a T is equal to 300 degree Kelvin. So if at a T is equal to 300 degree Kelvin, my Ni is how much? It is 1.5 into 10 raised to 10 per centimeter cube for silicon. Okay, for silicon. So it's going to be, so 10 raised to 11 is very close to 10 raised to 10, so it is very near to EFI. Okay, and then it will increase like this. It will go very near to the conduction band at heavy doping. Okay, now our Boltzmann approximation breaks down somewhere here. Okay, so somewhere here we cannot use our Boltzmann approximation, so that we have to be careful. So in this range, Boltzmann approximation is not valid. Okay. But till then, you can show that it is as so. Here it is in a exponential way. I am showing. Okay. The doping concentration is increasing by 10 times when I move one distance. So then EF is going to change like this linearly. But once the Boltzmann approximation breaks down, okay, so this line is not very accurate. Okay, so you have to show like this. So that is the dependency of Fermi level with doping concentration, because in the extrinsic regime there is a increase in EF going closer and closer to EC from EFI. Okay, EFI is the intrinsic Fermi level. Okay, so that is what this expression is also suggesting. Okay, EF minus EFI is going to increase with N0 going above Ni. So N0 is going to be determined by Nd, right? So as Nd increases, then it will become larger and larger, and finally it will come closer. It can even go inside EC, okay, above EC also. That is also plausible. So at very large concentration, it will go inside or above EC. So certain devices are there which is very heavily doped, which has EF going inside or inside the conduction band. Okay, so that is also physically possible. And similarly, I can talk about how the Fermi level changes with temperature. Okay, so x-axis if you take temperature, and then you have to fix your doping concentration, so that also I can show. So this is, so now I will take temperature on T in degree Kelvin on x-axis. So I will have 100, 200, 300, 400, 500, 600. Okay, so these are the temperature. If I take an n-type, so let me take EF here. So this is my EFI. Let's assume that I have doped it with so EC is somewhere here. So if I have doped it with say 10 raised to 16, so let's say ND is equal to 10 raised to 16 per centimeter cube, and Na I am taking it as 0. So it's n-type material. So at very low temperature, then let's skip that, and let's say at room temperature, let's say at room temperature, what will going to happen? It will be much above EFI, somewhere in between. Okay, so somewhere here it will be. And as you increase the temperature, what will happen? It will become more and more intrinsic. So this is it will tend to go to intrinsic at very large temperature, because at around 500 degree or 600 degree Kelvin, intrinsic concentration also become comparable to 10 raised to 16. So that is when it becomes intrinsic. Okay, so if I draw this, so you will have so what it suggests is that, so you have 10 raised to 16 ND, and as you now cool it down, this will go more and more closer to the conduction band. Okay, it actually lies between conduction band and so there is an ED level here. Okay, somewhere here. So there is ED. So Fermi level lies between ED and it will lie between ED and EC at very low temperature. Okay, only then you can say that, you know, all the charges in the band structure, which if I show once again, so this is the valence band, and this is the conduction band, and this is our ED level. So all the electrons at if you look at 0 degree Kelvin, all the electrons will be here. None will be going away from the donor impurity atom, and absolutely filled valence band and absolutely empty conduction band. So this will be the picture, and if this picture has to be satisfied, then our Fermi-Dirac function should with respect to energy, it should look like this. Everything filled till your donor impurity level, so it should be above. So the EF should lie. So this is this point is EF. Okay, where Fermi-Dirac function f of E is 1 here, and it is 0 here. Okay, so if it has to be filled completely, then it should be 1 above ED, and then 0 for conduction band to be completely empty, it should be 0 here. So Fermi-Dirac function will be a step function for 0 degree Kelvin. Okay, so this is T equal to 0 degree Celsius. So that is why I am showing here, I am showing EF on this y-axis for this graph and with respect to temperature. So it will become intrinsic at some high temperature where our Ni becomes equal. So at this point is basically N0 is almost equal to Ni, because Ni has become so much larger that the value of N0 is entirely determined by Ni, okay, not determined by the but in the middle region you have N0 equal to N0 equal to Nd, okay, so that is middle temperature. But in the intrinsic region, N0 is determined mostly by Ni. Okay. Here Ni is negligible, so we don't consider. So in that quadratic expression, if you leave your Ni, it will be called Nd. So this is the dependency of Fermi level with respect to temperature, and the above graph shows the dependency of the Fermi level, how it varies with the doping concentration at a fixed temperature. Okay, so these are the things that you need to know for the understanding of the working of the device. Even if it is a diode, if you don't know these things, you will not understand the band diagram of a diode. So alright, I will stop here.